Hello, in this review video, we're going to be talking about the IB physics content that you absolutely positively want to know walking into the IB exams. All right, this should cover some of the really key ideas that you definitely want to know and understand going into the exams. All right, this is in addition to, of course, knowing your whole data booklet inside and out. That's maybe the most important thing, but I'm going to highlight just some of the key concepts. So this is where you want to start. All right, start here and then you go from here. But these are some really important key ideas that you would definitely not want to have any confusion about going into the exams. So here's my tips for you. Here we go. The most important thing by far to know about physics is the whole deal with work and power. All right, these are foundational to every single unit. They come up all the time. So, of course, work is our first definition, maybe the most important definition, definitely one of them. Work is the transfer of energy, all right? Work is an amount of energy. Really, that's the definition of work. Work is delta E. It's the change in energy, how much energy gets added to a system, how much energy is taken away by friction. All of these different scenarios, how much work is done on a piece of copper to heat it up by 3 degrees Celsius, whatever. All right, so work is change in energy. That's the definitions. That's the most important thing to think about. There is an equation in the data booklet for work, which is work is force times S times cosine of theta. Remember, theta is the angle between your force and displacement vectors in their equation. That's useful, but much more useful is the actual definition equation like this. All right, so this is if you know the size of a force and the displacement over which the force acts and the angle between the force and the displacement, you can figure out how much energy is deltaed. But this is the foundational concept you want to always think about and understand with work. Do some practice with work. Power is the rate of the transfer of energy. It's the rate at which work is done. A watt is a joule per second is the most important unit definition you can possibly know in IB physics. So this is the official definition of power. Again, not exactly in the data booklet. Somewhere in topic 8, it says power equals energy over time, which is close enough. But you're going to look in topic 2 and see F times V and screw it up if you don't know that this is what power is, especially. All right, so power is the rate at which you change energy, joules per second, change in energy over change in time. That's what power is. You absolutely need to know these, practice these, know these super well. These come up all the time. So work and power are those two things. Okay. Another really important definition that ties in like the electric side of things is, what is a volt? And so the best probably definition for this is to look at what potential difference is. Electric potential difference. It's work per unit charge, officially to move a charge between 2 points in an E field. Know that whole definition. Put it on the list of 100 definitions you want to know. That's a key one. But work per charge, the key idea, there's this equation and there's this equation. In different places, they're both the same equation, just written with different notation. Topic 10 is a little more official to show delta VE for electric potential difference, but it means the same thing. All right, so voltage is work over charge. Same thing here, right? Or charge times volts equals the amount of work that's done if you're talking about a potential difference that you move a charge through. All right, so a volt is a joule per coulomb, second most important unit definition to possibly know. Make sure you're okay with these equations, how to use them all the time. They're going to give you like an electron goes through a potential difference of 500 volts and find its kinetic energy. They got to know you can figure out the work that the field did on the charge by multiplying the potential difference by the charge. All right. It comes up all the time, right? A volt is a joule per coulomb is not just for this one equation. Like the definition of EMF has something to do with the work done by a battery per unit charge and driving charge throughout the whole circuit or something like that. You could talk about, if you want to talk about what does it mean that there's 3 volts that I measure across a resistor with my multimeter, well, that means that every coulomb of charge that flows through dissipates 3 joules of energy as heat, right? So thinking about what 1 volt equals 1 joule per coulomb is another good concept to wrap your head around. But there you go. A volt is a joule per coulomb. Know it. Field stuff. All right, so fields can be confusing, but make sure you focus on the basics at least. So remember, field strength is always a force per something. E field strength is force per unit charge. So you got this equation in topic 5. It's the electric force divided by the charge feeling the force. So that tells me newtons per coulomb. For every coulomb of charge that I put at this point in space, how much force would that amount of charge experience? Remember, field, there is no pushing or pulling happening with a field. It's describing the space and what would happen if I put a charge there. How strong would it be pushed or pulled? Therefore, you can find the electric force by multiplying charge by E field strength. All right, so you got to know that you can, of course, do that with this equation. And the gravitational field strength, same thing, but it's force per unit mass, so it's force over m. So this is why we get the equation Fg equals mg. Remember, g is only 9.8 or 10 on like a paper one, especially. On the Earth's surface, if you're doing anything in space, in the atmosphere, outside of the Earth, you got to use the equations in the data booklet for g that include the big G and an m over r squared, all that fun stuff. All right, but there you go. You can plug in lug here to get that equation. So you can put in big G times m over r squared. See, one of the m's cancels out. That'll give you the formula for calculating G when it's not 9.8. You can do the same thing for E, but that one's actually in your data booklet, which is nice. All right, and B fields, this has nothing to do with magnetism. With none of these equations should you be thinking about your right hand at all. You don't use a right hand rule unless it's a magnetic force situation and there's a magnetic field doing stuff. So this all has nothing to do with the magnetic field. Make sure you're cool with electric fields and what they show in terms of direction. It's the easier one, but make sure you understand what the direction of these fields means as well. All right, and don't confuse E fields and B fields at this point. To review E fields and B fields, I encourage you to check out the classic crossed fields problem. They're everywhere. Good chance you'll see this on the IB exams. They love this. It's a great one because it shows, if you can do this problem, you're showing that you understand the difference between electric fields and magnetic fields. So this is a really good review problem. Make sure you're cool with the difference between, this is an electric field that would maybe take a positive charge and push it down. But then if this is my magnetic field, a separate field, totally different thing, right? If I have a charge moving through a magnetic field that feels a force this big, officially QVB sine of theta, make sure you're okay why the sine of theta term drops in this example. But there you go, you got your magnetic field in the page, so there's going to be a magnetic force this way. That's when you use the right-hand rule, only for a B force, a magnetic force, nothing to do with the electric force. So make sure you know the difference between those two forces and how the cross fields problem works. All right, circuits. The key thing I would say to focus on for circuits, because there's a lot, energy and power. Here's some key things. This is a common one. The power equation in your data booklet in topic 5 looks like this. It's a bunch of different things. Generally speaking, this is kind of a general rule. It's not always the case, but general rule of thumb. I times V, V times I to get power, electrical power. That kind of is usually for the battery. So if you're talking about a battery or a source like a cell or something, this can tell you how much power is provided, the voltage across the battery times the current that is pushing out, something like that. And I squared R is usually for dissipation. Dissipated energy is heat, like power lines or a resistor. How much energy does it give off as heat? Because you're talking about the current flowing through some resistance. That's pretty general. All right, but know your power equations, and if you see internal resistance, there's a good hint. That means you have to use this equation. This is the equation that deals with electric cells and deals with the resistance inside of a battery. So if it says ideal cell, you don't worry about this. But if it says internal resistance, this is the equation in the data booklet that has internal resistance. You got to know, like, little r is internal resistance of like a battery. Big R is the total resistance of your whole external circuit then. So if you know your data booklet, you know that this is the only place where internal resistance shows up. So if you got internal resistance and you got in math, this is the equation you got to use. All right, remember that's how we picture that the battery contains some ideal cell of EMF E and internal resistance little r, and it's hooked up to whatever's going on with the rest of the circuit where I can actually do some measurement. Also make sure you're okay with the different versions you can turn this equation into. I could distribute the I and get I times big R is really V. The V I would measure out here. I times little r goes out here. So this is one version of the equation. So is this. This is a common one because notice this is a linear equation. So you can make a graph of V versus I, for a circuit and measure like the internal resistance of a battery by getting different, really you do this by getting different R's, big R's, right? Hook up your battery to different big resistors. You'll see the voltages across the battery that you get at different currents, and you could plot V versus I. Your y-intercept would be the EMF, and your slope would be negative internal resistance. All right, so make sure you know this equation and like how it can show up on a graph and this picture of a battery. All right, some other key core topics. Greenhouse effect. Make sure you know the greenhouse effect. Know like the 4 steps to it, and the most important thing is know these vocab terms. Make sure you don't say reflect. The greenhouse gases, what they do is they absorb and re-radiate specifically infrared light that the Earth gives off because of resonance. They resonate at that infrared frequency. So know the whole deal that the sun gives off visible light, which the greenhouse gases don't really care about, but then the Earth, because it's much cooler, gives off infrared. So that's what gets absorbed, re-radiated, sent back down towards the planet, trapped in a way, if you will. All right, those are key terms. Simple harmonic motion, like all of this, it's a whole thing, but if you want to pick one most important thing, know the definition. This graph is the definition of simple harmonic motion. Think about why. But this graph defines simple harmonic motion, so you want to know acceleration is proportional to displacement, and they're always in opposite directions. If I'm displaced to the right, my acceleration is to the left, and vice versa, and that's what makes it do simple harmonic motion. So know this as your definition, and then practice all the fun sine, cosine stuff. All right, and for HL, just a couple key topics to focus on. All right, for fields, one first thing is you might see this graph. This is a good graph to memorize because there's a bunch of graphs like this in IB physics. But if you see like a potential versus distance graph, a V versus R graph, you know the only thing you're going to do with that graph is you're going to draw a tangent line, take the slope, and the slope is the size of your field strength. All right, that's like a rule from the data booklet. So if you have this graph in joules per kilogram versus some kind of distance, the slope would be your field strength, your gravitational field strength, since I'm talking about per kilogram. If it was per coulomb, it would be electric field strength. Right? Remember how to do gradient? You draw a tangent line at the point you care about, so I could find the field strength at a distance of 2 like planet radiuses, I'm guessing, away from the planet, from the center. And the slope of this line is the gradient. So gradient means slope of a tangent line at the point you care about, right, on the x-axis. All right, and do study the big scary table. Remember this guy, topic 10? You want to know at least what all those terms mean. You got to know the difference between potential and potential energy, and even potential difference, field strength and force, all that stuff. So here's a quick handy little reference for you. Focus on the units for this. Remember, units don't make an equation, but they'll help you think about at least what the thing is. Hopefully you know which of these are vectors and which are scalars, 2 of each on each side of the table, right? But study all this. Make sure you know for sure, just truly like what the names of these things are is bare minimum, right? So you got to know that that's electric force. You got to know that's electric field strength. So we would measure newtons per coulomb. That's potential energy versus that's potential. Yeah, so just know what all of this stuff is. Here's the clue that this rule happens, right? This says G is the gradient of VG versus R. The delta over delta is your hint. All right, so study that table, know what everything is, so you can at least know what equation to pick and don't mix up like this equation and this equation because they're totally different things. All right, topic 11 is a doozy. Topic 11, pick and choose, all right? 11.2 and 11.3 are very, very doable, especially if you're okay at circuits. Because it's just like 11.2 is all just, divide stuff by square root of 2, and then it's all your same equations. Power equals I times V. Transformers are easy. It's just ratio problems, so just know how to read this equation and remember what goes on what side and practice a few of those. This stuff, not too bad at all. Capacitance, great fun. Exponential decay stuff is about as bad as it gets. Even a lot of this stuff is pretty basic. You got the same like parallel and series kind of similar rules. They're just flipped from what you're used to for resistors, so just know those. This is like the area of the plate's capacitance stuff, energy stored in a capacitor. If you know what these equations are, you can handle the problems 90% of the time. They really don't get too hard. 11.1 electromagnetic induction is the double black diamond of IB physics. So stay away from this unless you're really, 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 really training hard at everything else. All right. There's very few equations here and they look very simple, but this is definitely the hardest stuff in this topic and maybe the whole curriculum. All right, so don't spend a lot of time here. Spend your time where you can get some points on 11.2 and 11.3. All right, and lastly, know of all the crazy quantum physics stuff, know the photoelectric effect. You're going to see this graph. You got to know that you can graph the maximum kinetic energy of photoelectrons versus frequency of incoming light and get a graph whose slope is Planck's constant and whose intercept is the negative work function. Make sure you understand the photoelectric effect equation, why that works, and also understand the photon model of light and how it helped to explain the specific details of the photoelectric effect. They love the photoelectric effect There's one, honestly, the only things we do in quantum physics where we can even remotely handle the math and concepts. So there's going to be a lot of good photoelectric effects stuff happening, so know the photoelectric effects really well. All right, and last then, just some general tips on test strategy. Because this is as important as the content is. This is one of the most important things too, sadly, but it's a standardized test, so get ready for it like a standardized test. The paper one, go in with the letter of the day. Don't waste any mental energy like debating what random answer to pick. If you get into your last 2 minutes and you gotta, pick some random answers, just go in with the letter. Say everything I don't know, it's gonna be B or whatever. All right, paper 2, you get 5 minutes up top of reading time. The first 5 minutes of the paper 2 are free 5 minutes. You're not allowed to touch your pencil, so you just read the exam. So page through your 90-something marks worth of questions and decide which ones you're going to attempt, because you might not get to everything. So identify the problems that you know how to do well and start with those. Don't get intimidated if you see some crazy EM induction thing. You just skip right over that until you got time at the end. Yeah, so make a game plan first. Of course, start with the problems you're confident about. Remember the guess method we've been using since freshman year. Start with your givens, identify your unknown, then pick an equation that will help you solve it, and then substitute and solve. So if you can just do good, problem solving strategy, underline the givens, make sure you know your data booklet really well so you know the E step, right? That's the part that you can go in really confident about. Study your whole data booklet. They say internal resistance, you're like, boom, I know what one equation to go to. Yeah. And keep an eye on your time. So don't get stuck on one problem for too long. You get about 1.5 minutes per mark, actually just a little bit less on the paper 2 even. So keep an eye on the timer. Don't get stuck on anything for too long. If you spend, 10, 15 minutes on one problem and you're not getting anywhere, you're leaving a lot of points on the table. So jump around, don't work in order. You can even use, remember, they'll do like the show that thing. They'll say in part A, they'll say, show that the field strength on the surface of Mars is, 3 point whatever. Then in part B, they'll ask you to do something with that value. The reason they give you show that is if you can't, or, even if you want to work out of order, if you don't get the answer to part A, but they say show that the answer is blah, 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 you can use that number in later parts of the problem. So if you're stuck on part A, but you need a value for part B, like use the show that answer to jump around. All right, so this is just another part of the whole same strategy, which is work in an order where you can maximize the amount of points you get and get to the most stuff. All right, so use all those little tricks in the thing. All right, and paper 3, just remember section A. This is a data section, so make sure you do this. Every once in a while, there's a horror story about a student who skips section A and goes right to astrophysics and only does astrophysics. You do have to do section A, and then you do option D for astrophysics. And know your astro. Astro, you get the most bang for your buck, believe it or not, because paper 3 is pretty much all astrophysics. So if there's one topic to really study and know, it's probably astrophysics. It might be mechanics too, but astrophysics, truly, you get the most bang for your buck. So if you know astrophysics really well, it can save your butt. All right, so there's some of my tips of the key stuff to know. There's a lot more to know than that, but that'll at least get you started. So get to it. All right, good luck and have fun.